Look up at the night sky. Every bright point you see, every star, is a massive ball of gas held together by gravity. Some stars are millions of times more massive than Earth, yet they hang in space for billions of years without collapsing. At first glance, this seems impossible. Gravity is relentless. It pulls everything inward. On Earth, gravity keeps us on the ground. On a cosmic scale, gravity pulls gas, dust, planets, and entire galaxies together. So the question naturally arises, if gravity is always pulling inward, why doesn't a star instantly collapse into a tiny, dense object? This question is not naive. In fact, it is one of the most fundamental questions in astrophysics. A star begins its life as a cloud of gas, mostly hydrogen, drifting through space. Over time, gravity causes this gas to clump together. The more gas that gathers, the stronger gravity becomes. This creates a runaway process. More mass equals stronger gravity. Stronger gravity equals faster collapse. Faster collapse equals higher density. If nothing resisted this inward pull, the gas cloud would collapse rapidly, heating up violently and forming a compact object almost instantly on cosmic timescales. Yet stars do not behave this way. Instead, they stabilize, they shine steadily, and they survive for billions of years. Clearly, gravity is not acting alone. Inside a star, something pushes outward. This outward force is called pressure. Pressure is not a mysterious concept. You experience it every day. Air pressure in your lungs, water pressure deep in the ocean, steam pressure in a pressure cooker. In stars, pressure arises from hot gas. When gas heats up, particles move faster. They collide more violently. These collisions push outward. This outward push directly opposes gravity. Inside every stable star, two forces are locked in a constant struggle. Inward force, gravity pulling all mass toward the center. Outward force, pressure pushing outward from the hot interior. This balance is not static. The star is not frozen. Instead, the star exists in a state called hydrostatic equilibrium. Hydrostatic equilibrium means at every layer inside the star, the inward pull of gravity is exactly balanced by the outward push of pressure. If gravity becomes slightly stronger, the star contracts. Temperature rises, pressure increases, and balance is restored. If pressure becomes slightly stronger, the star expands. Temperature drops, pressure decreases, and balance is restored. This self-correcting feedback is why stars are stable for so long. What makes this balance extraordinary is the scale involved. Consider the Sun. Mass approximately 2 × 10 to the 30 kilograms, core temperature approximately 15 million Kelvin, core pressure approximately 250 billion atmospheres. Yet this enormous system remains stable because forces cancel almost perfectly. The Sun is not about to collapse. It is not about to explode. It simply shines. Stars do not collapse instantly because gravity pulls inward, pressure pushes outward, and these forces balance through hydrostatic equilibrium. But this only answers how stars remain stable, not where the pressure comes from in detail. To understand that, we must go deeper. Pressure inside a star does not come from a solid surface or rigid structure. Stars are plasma, hot ionized gas. To understand stellar pressure, we must understand temperature and motion. In physics, temperature is not just hotness, it is a direct measure of particle motion. Higher temperature means faster particles, more energetic collisions. Inside a star's core, hydrogen nuclei move at enormous speeds. Collisions occur trillions of times per second. Each collision exerts a tiny force. Add them together across the entire star, and you get immense pressure. For much of a star's life, its pressure can be approximated using the ideal gas law. P equals N times K times T, where P equals pressure, N equals number density of particles, K equals Boltzmann constant, and T equals temperature. This simple equation explains something profound. Hotter stars push harder against gravity. When gravity compresses gas, density increases, collisions increase, temperature rises. This is known as gravitational heating. Paradoxically, gravity, which we associate with collapse, actually creates the pressure that resists collapse. Gravitational heating alone is not enough to keep a star shining for billions of years. At sufficiently high temperatures, something extraordinary happens. Nuclear fusion ignites. In the core, hydrogen nuclei fuse into helium, a small amount of mass converts into energy, and energy flows outward. This energy maintains high temperatures, sustains pressure, and prevents collapse. Fusion acts like a thermostat. If the core cools, fusion slows, contraction, reheating. If the core overheats, fusion speeds up, expansion, and cooling. In massive stars, pressure does not come only from particle motion. Light itself exerts pressure. Photons carry momentum. When they strike matter, they push. In very massive stars, radiation pressure becomes significant. It can rival gas pressure, and it helps prevent collapse. This is why massive stars behave very differently from small stars. Larger mass, stronger gravity, higher core temperature, faster fusion. As a result, massive stars burn fuel rapidly. They shine brighter, they die younger. Small stars burn slowly and live longer. Stars are stable not because gravity is weak, but because gravity creates the conditions that resist itself. However, this balance cannot last forever. Eventually, fuel runs out. And when that happens, the universe reveals some of its most extreme physics. A star's stability depends on energy production. When fusion slows or stops, pressure weakens. Gravity never weakens. Hydrogen is the primary fuel of most stars. When hydrogen in the core is exhausted, fusion rate drops, energy output decreases, pressure declines. Immediately, gravity gains the upper hand. As the core contracts, temperature rises again, fusion may restart in surrounding shells. The outer layers expand. This produces red giants, supergiants. The star is no longer in simple hydrostatic equilibrium. What happens after fusion can no longer generate pressure. This is where new forms of pressure appear, ones that have nothing to do with temperature. Quantum mechanics enters the story. Up to this point, pressure has come from heat, moving particles colliding and pushing outward. But nature has a problem. Eventually, a collapsing stellar core becomes so dense that temperature no longer matters. Yet, collapse still does not always continue. Something else intervenes. This is where quantum mechanics takes control. When nuclear fusion ends in a stellar core, temperature can temporarily rise due to contraction, but no new energy source exists. Heat radiates away. At sufficiently high density, electrons are packed extremely close. Classical gas laws break down. Pressure no longer depends on temperature. This regime cannot be explained by classical physics. No two identical fermions can occupy the same quantum state. Electrons are fermions. As gravity squeezes a stellar core, electrons are forced closer together. Available quantum states fill up. Electrons are forced into higher momentum states. This creates pressure purely from quantum rules, not heat. This is called electron degeneracy pressure. This pressure does not rely on temperature, fusion, or energy generation. It arises because nature forbids further compression without increasing momentum. Even at absolute zero, degeneracy pressure remains. This is profoundly counterintuitive. A star can resist gravity without being hot. When a sun-like star exhausts its fuel, outer layers drift away, the core contracts, and electron degeneracy pressure halts collapse. The result is a white dwarf. Typical properties: mass approximately 1 sun, radius approximately 1 Earth, Density approximately 1 million grams per centimeter cubed. Matter here is nothing like ordinary matter. Atoms no longer exist. Electrons form a degenerate quantum gas. Nuclei float in a dense sea of electrons. White dwarfs behave strangely. More mass to smaller radius, less mass to larger radius. This is opposite to normal objects. The reason is purely quantum. Higher mass, stronger gravity to higher electron momentum, higher momentum to higher pressure. This relationship was first derived by Subrahmanyan Chandrasekhar. There is a maximum mass electron degeneracy pressure can support. This limit is approximately 1.4 solar masses. If a stellar core exceeds this mass, electron degeneracy pressure fails, collapse resumes. This limit is not empirical. It comes from combining quantum mechanics, special relativity, and gravity. It marks a fundamental boundary of nature. References: Chandrasekhar, S., 1931, The Maximum Mass of Ideal White Dwarfs. Shapiro and Tucholsky, Black Holes, White Dwarfs, and Neutron Stars. When electron degeneracy pressure fails, collapse accelerates violently. But gravity does not immediately win. Matter transforms. At extreme densities, electrons are forced into nuclei. Protons capture electrons. Neutrons are formed. This process is called inverse beta decay. P plus E negative, arrow N plus nu E. Neutrons escape, carrying energy away. The core becomes dominated by neutrons. Neutrons are also fermions. They obey the Pauli exclusion principle. As neutrons are packed together, quantum states fill, momentum increases, and a new degeneracy pressure arises. This pressure is far stronger than electron degeneracy pressure. A neutron star forms when collapse is halted by neutron degeneracy pressure. Typical properties: mass approximately 1.4 to 2 solar masses, radius approximately 10 to 12 kilometers, density approximately atomic nucleus. A teaspoon of neutron star matter would weigh billions of tons. Neutron stars are supported by neutron degeneracy pressure and repulsive components of the strong nuclear force. At these densities, gravity, quantum mechanics, nuclear physics are equally important. This makes neutron stars natural laboratories for extreme physics. Neutron degeneracy pressure also has a limit. Above a certain mass, even neutrons cannot resist collapse. This theoretical boundary is called the TOV limit, roughly MTOV, approximately 2 to 3 M solar. The exact value depends on the unknown equation of state of ultra-dense matter. When all known forms of pressure fail, thermal pressure, radiation pressure, electron degeneracy, neutron degeneracy, gravity remains. But gravity is no longer just a force. According to Einstein, mass energy curves spacetime. Objects follow curved paths. In extreme collapse, spacetime curvature becomes dominant. No pressure gradient can counter it. The equations governing this regime are the Einstein field equations. G mu nu equals 8 pi g over c to the fourth T mu nu. Here, geometry responds to energy. Collapse becomes geometric inevitability. A black hole does not form because gravity becomes stronger. It forms because no physical process can generate an outward pressure. Escape velocity exceeds the speed of light. Causality itself collapses. The event horizon is not a surface, it is a boundary in spacetime. Even black hole formation takes time from an external observer, proceeds through layers, and is governed by relativistic causality. Collapse is never instantaneous. The universe forbids it. References: Einstein, 1915, General Theory of Relativity. Oppenheimer and Snyder, 1939, on continued gravitational contraction. Wald, General Relativity. Pressure is not merely resistance to gravity, it creates gravity. In Einstein's theory, gravity is sourced not only by mass, but the entire stress-energy tensor, T mu nu. This tensor includes energy density, momentum flow, shear stress, and pressure. This leads to a disturbing conclusion. Pressure itself gravitates. Inside a star, pressure resists collapse locally, but globally, pressure increases space-time curvature. At extreme densities, adding pressure can actually accelerate collapse. In Newtonian physics, hydrostatic equilibrium is simple. In relativity, it becomes the Tolman-Oppenheimer-Volkov equation. dP dr equals minus g times rho plus p over c squared times m plus 4 pi r cubed p over c squared over r times r minus 2 gm over c squared. This equation encodes a deep truth. Pressure contributes to gravity. Gravity feeds back on pressure. Stability becomes nonlinear. At high compactness, equilibrium becomes impossible. An equation of state relates pressure to density. At low densities, gas laws apply. At higher densities, degeneracy pressure dominates. At nuclear densities, strong force repulsion appears. But relativity imposes a limit. As r approaches 2 gm over c squared, the denominator shrinks. No finite pressure gradient can halt collapse. This is not about insufficient force, it is about geometry becoming singular. Despite inevitability, collapse does not proceed arbitrarily fast. The reason is causality. In relativity, information propagates at or below c. Pressure changes propagate as sound waves. Sound speed is always less than c. Thus, outer layers cannot know instantly what the core is doing. Collapse proceeds shell by shell. This alone forbids instantaneous collapse. As space-time curves, light cones tilt inward. Possible future paths shrink. Near horizon formation, all future-directed paths lead inward. Outward pressure loses causal influence. This is not force failure, it is loss of future options. During collapse, trapped surfaces form first. Apparent horizons emerge locally. Event horizons are defined globally. This distinction matters. Locally, matter still evolves normally. Globally, escape becomes impossible. The star collapses without locally noticing the horizon. Popular language describes singularities as points. This is misleading. A singularity is not a place, not a thing, not a particle. It is the breakdown of space-time description. Mathematically, curvature invariants diverge. Geodesics end incompletely. Physics stops making predictions. These theorems show if gravity is attractive, energy conditions hold, and trapped surfaces form, then singularities are inevitable. No material property can prevent this outcome. Not pressure, not forces, not quantum statistics at classical level. From the perspective of external observers, collapse slows near the horizon. Time dilation increases infinitely. The star appears frozen. From the infalling matter's frame, collapse continues. Proper time remains finite. There is no universal instant of collapse. At sufficiently small scales, general relativity predicts infinities. Quantum theory forbids them. These theories are incompatible here. At densities near rho, p-L-A-C-K, approximately 10 to the 94 grams per centimeter cubed, space-time fluctuations dominate. Classical geometry loses meaning. Pressure, force, and even distance become ill-defined. Even here, quantum interactions are local. Causality still constrains evolution. No signal propagates infinitely fast. Instant collapse would require infinite signal speed, infinite force, infinite coordination. Nature forbids all three. Does quantum gravity halt collapse? Do singularities truly form? Is there a bounce? Does space-time tear or transition? No experiment has answered these. At every scale, collapse is resisted, then delayed, then transformed. Not stopped by strength, but by rules. Rules of statistics, causality, geometry, and quantum structure. Gravity never acts alone. Gravitational collapse is often imagined as a mechanical failure. Pressure fails, gravity wins. This picture is incomplete. At a deeper level, collapse is driven by thermodynamics. Most physical systems evolve toward maximum entropy. Gravity behaves differently. Uniform matter has low gravitational entropy. Clumped matter has higher gravitational entropy. A star is already clumped, but not maximally. Collapse increases density contrasts, curvature contrasts, phase space occupation. From a thermodynamic viewpoint, collapse is favored, not resisted. Pressure organizes motion. Entropy favors disorder. Thermal pressure redistributes energy, smooths gradients, and temporarily stabilizes structure. But it does not reduce gravitational entropy. Thus, equilibrium is metastable, long-lived but not permanent. Stars are thermodynamic compromises, not final states. Self-gravitating systems have a bizarre property. They heat up when they lose energy. If a star radiates energy, the total energy becomes more negative. The core contracts and temperature increases. This violates everyday intuition but is unavoidable for gravity. This guarantees instability at long timescales. Collapse is not just matter moving inward, it is information being redistributed. Pressure waves carry energy, momentum, and information. They propagate at the speed of sound, not instantaneously. As density rises, mean free paths shrink, communication slows, and local regions decouple. Collapse fragments causally. When trapped surfaces form, outgoing signals fail. Internal states become hidden. This is not destruction of information, but causal separation. The interior continues evolving, but the exterior cannot access it. No global command exists. Each shell responds only to local curvature, local pressure, local causal past. This enforces gradual collapse even under extreme gravity. Instant collapse would require infinite accelerations, discontinuous fields, non-local coordination. All are forbidden by relativistic field theory. Every interaction, electromagnetic, nuclear, gravitational, propagates at finite speed. Even gravity propagates as curvature changes, limited by light cones. No part of a star can respond infinitely fast. The conservation law, delta mu T mu nu equals 0, enforces continuity. Sudden collapse would violate energy conservation, momentum conservation, and causal continuity. The equations themselves forbid it. From outside, collapse slows, time dilates, redshift diverges. From inside, nothing special happens locally. Physics remains smooth. Proper time flows normally. There is no universal clock. Instant has no invariant meaning. Collapse occurs over finite proper time, infalling matter. Infinite coordinate time, distant observer. Both descriptions are valid. Neither allows instant collapse. Stars appear stable because timescales are long, feedback loops are strong, human lifetimes are short, but stability is local and temporary. At deeper scales, every equilibrium is conditional. Every balance depends on assumptions. Every pressure has a limit. Why don't stars collapse instantly? Because collapse is not an event. It is a process, governed by layers of rules. There is no switch, no failure point, no moment of surrender. Only gradual loss of options. By this stage, it becomes impossible to separate gravity from thermodynamics. This is not analogy, it is literal. Event horizons possess temperature, entropy, and laws resembling thermodynamics. This was first revealed through black hole physics, but the lesson applies earlier. Any sufficiently compact object develops horizon-like behavior, information loss across causal boundaries, irreversibility, increase in entropy. Collapse is guided not only by equations of motion, but by entropy accounting. Gravitational entropy scales with area, not volume, S proportional to A. This contradicts ordinary matter behavior. As a star collapses, volume decreases, surface curvature increases, horizon area eventually dominates. Collapse proceeds in the direction that maximizes accessible area, not density. Pressure resists compression locally. Entropy favors larger horizons, larger causal disconnection, greater inaccessible information. At high compactness, entropy gradients overpower pressure gradients. The star collapses because geometry wants more entropy. Some modern theories suggest gravity is not fundamental. It emerges. In emergent gravity models, space-time curvature arises from information distribution. Forces emerge from entropy gradients. Collapse then becomes reorganization of information, flow toward maximal entanglement. Pressure cannot halt this because pressure is subordinate to information structure. If gravity is emergent, equilibrium corresponds to local entropy plateaus. Global entropy gradients persist. Stars are local minima in a larger entropy landscape. Eventually, gradients reassert, structure dissolves, collapse resumes. Matter inside stars is not classical. It is quantum fields living on curved backgrounds. Quantum vacuum contains fluctuations, virtual particles, zero-point energy. In strong curvature, vacuum structure distorts, particle definitions change, pressure calculations become frame-dependent. Quantum fields react to curvature, energy densities shift, stress energy changes, geometry responds. This feedback destabilizes static solutions. Perfect equilibrium becomes mathematically impossible. Quantum mechanics does not prevent collapse. It delays it. Heisenberg uncertainty increases momentum spread. This creates pressure-like effects, but also increases energy density. At extreme confinement, quantum effects enhance gravity, not suppress it. Confining matter increases energy uncertainty, increases stress energy, deepens space-time curvature. Quantum mechanics accelerates geometric consequences. No observer accesses the whole collapse. Each observer lives inside a causal diamond. Inside each causal diamond, physics appears ordinary. No singular behavior. No infinite forces. Collapse looks smooth and continuous. What we call stellar collapse is a stitching of local evolutions, governed by causal overlap, never synchronized. Instant collapse would require global simultaneity, which relativity forbids. Fast catastrophes release energy efficiently. Gravity prefers the opposite. Gradual collapse allows energy leakage, increases entropy outside, preserves conservation laws. Instant collapse would trap energy too efficiently. Nature avoids it. Not fastest, not strongest. Collapse follows allowed paths, maximum entropy growth, causal consistency. From gas clouds to black holes, resistance appears. Limits are reached. New rules activate. Collapse is not stopped. It is refracted through layers of law. Long before a star becomes a black hole, it already obeys holographic limits. These limits are not optional. They are fundamental. The holographic principle states,
The maximum information inside a region scales with its surface area, not its volume. This idea is usually associated with black holes, but it applies everywhere. Inside a star, matter stores information, fields store information, geometry stores information. As collapse proceeds, volume shrinks faster than area. Information density rises. Degrees of freedom are compressed. Eventually, the star approaches an information bottleneck. Pressure limits how fast information can be packed. Degeneracy pressure limits phase space occupation, enforces quantum bookkeeping. But holographic bounds are stricter. When information density approaches surface limits, new behavior emerges. Classical intuition fails. Collapse is redirected, not halted. Before an event horizon exists, entropy is still be redistributed. Nothing is hidden yet. This stage is crucial. During late-stage stellar evolution, radiation escapes. Neutrinos carry entropy. Outer layers absorb disorder. The collapsing core exports entropy outward. This is why collapse is slow. Instant collapse would trap entropy internally, prevent radiation, and reduce total accessible entropy. This is forbidden. The second law enforces gradual collapse. A horizon separates causal regions, limits information flow, and redefines entropy counting. Once a horizon forms, interior entropy becomes inaccessible. Exterior entropy accounting changes. Only then can collapse accelerate. Pressure requires communication, response, and feedback. Near a horizon, signals cannot propagate outward. Pressure gradients lose influence. Geometry dominates. Support mechanisms lose meaning. Singularities do not drive collapse. They signal incomplete description, missing degrees of freedom. Collapse reaches a point where geometry cannot encode information smoothly. The theory breaks. The singularity is a diagnostic, not a destination. Time behaves strangely in strong gravity. Different regions experience different clock rates, different causal horizons. There is no single time parameter governing collapse. Instant becomes meaningless. Synchronization requires signal exchange, shared frames of reference. Strong curvature destroys both. As collapse deepens, sensitivity to initial conditions increases. Microscopic fluctuations amplify. Predictability degrades. This is not chaos in the usual sense. It is information starvation.
The equations remain deterministic, but inputs are unknowable, outputs diverge, measurement becomes impossible. Collapse proceeds beyond observational reach. No state in known physics is truly final. Even black holes evaporate, radiate, and lose information access. Stars do not collapse instantly because absolute states are disfavored. Gradients must persist. Evolution must remain local. Collapse does not finish. It transitions between descriptions, between effective theories, between observers. Each layer ends where the next begins. Even before horizons form, stars employ subtle mechanisms to delay collapse. Energy and entropy leave the core via photons and neutrinos. Neutrinos are weakly interacting, escaping easily from dense cores. This flux carries away energy, temporarily reducing gravitational dominance. Collapse is not abrupt because nature prefers paths that maximize accessible entropy. Sudden compression would trap energy and reduce accessible states. By exporting entropy slowly, stars ensure thermodynamic consistency. During late stages, shell burning or degeneracy pressure can produce temporary plateaus of stability. Each plateau lasts thousands to millions of years. Stars appear frozen externally, but slowly, entropy redistribution prepares the next contraction phase. Once the core reaches critical compactness, locally, regions form where all light rays point inward. Pressure gradients no longer communicate with outer layers. Horizons are causal boundaries, not physical walls. Exterior observers see collapse slow due to gravitational time dilation. Interior observers still fall normally toward increasing density. Collapse is gradual locally, instantaneous externally is impossible. This preserves the relativistic causal structure and ensures physical laws are never violated. At extreme densities, vacuum fluctuations interact with strong curvature. Energy densities shift dynamically. Geometry and quantum fields co-evolve, slightly delaying collapse. Confinement increases momentum uncertainty. Electron or neutron degeneracy pressure rises, temporarily resisting contraction. Even here, these mechanisms only postpone the inevitable. They cannot prevent collapse indefinitely. Hawking radiation is negligible at this stage, but theoretically exists. Quantum effects introduce subtle thermodynamic corrections, smoothing the collapse profile. Eventually, thermal pressure exhausted, degeneracy pressure maxed out, radiation pressure irrelevant. At this point, classical and quantum resistances fail and collapse accelerates. The horizon hides the singularity from external observers. From the outside, the star appears frozen indefinitely. From the inside, matter continues falling toward extreme curvature. Singularity signals breakdown of current physics. Nature does not create infinite density instantly. Instead, space-time reaches a boundary of description. After journeying from gas clouds to singularities, the picture becomes clear. Multiple layers resist collapse. Thermal pressure, radiation, degeneracy, and nuclear forces all contribute. Collapse is constrained by causality. No influence can propagate faster than light. Entropy governs the pace. Stars export disorder gradually to maintain thermodynamic consistency. Quantum and relativistic rules intervene. Pressure becomes geometric or statistical. Horizons form, slowing external observation. Stars do not collapse instantly because nature layers resistance, causality, thermodynamics, and quantum rules, producing a slow, structured process instead of a catastrophic failure. Even in collapse, the universe enforces gradual, lawful evolution rather than instantaneous chaos.